Dr. Chandrasekhar. Good evening, everyone. I am myself, Dr. Chandrasekhar, Joint Secretary ISPR. I welcome ISPR Executive, including Dr. Suresh Kulkarni, President, and Dr. Ajit, Secretary. After stupendous success of our first two master classes on vascular access and hardware, we are here for our third installment, which is an important topic of stents. As you know, stents were developed in the mid-80s, and since then there have been major refinements in design and composition. Despite being used for decades, stents still have a considerable research potential. Without wasting much time, I'm pleased and honored to introduce our esteemed master faculty, Dr. Rochan Pant. He needs no introduction. He is currently working as consultant intervention radiologist at Reliance Foundation Hospital, Global Hospital, PD, Hinduja National Hospital, Mumbai, Jahangir, Pune, and Dinanath Mangeshkar Hospital, Pune. He has been the past president and vice president of ISPR. He has won many awards and accolades, including Visist Seva Medal from President of India. And he did his MBBS and MD from FMC Pune and specialty training in IR from Bombay. And he has been teacher and examiner for many DNB examinations. And he will be speaking on various aspects of stents, including advances. Over to you, sir.
Thank you. I trust everybody can hear me and see the screen. Right.
Yes, sir.
So stents are very well known to us. I think most of us are aware what stents are. The word stent comes from the name of a English dentist who used this plastic substances to create a scaffold for repairing bones and teeth. That's where the word stent comes from. However, for us, and stents are implants that we use to keep various ductal structures open. But today I'll be mainly talking about vascular stents because that's the area with the most, shall I say, research and development potential. Though, of course, those development potentials and those research areas also extend to non-vascular stents. And I will talk a little bit about them as time comes up. So I'll be talking about this particular issue. Okay. So why stents? Now, daughter did an angioplasty in on the 16th of January in the early 1980s. And the lady called Laura Shaw, who was the first person to undergo angioplasty, was the beneficiary of that procedure, which brought about a revolution in the treatment of vascular disease. And angioplasty was earlier done by using serial dilatation and then converted to balloon angioplasty by Andreas Grunzig, which led to the company called Schneider Manufacturing Balloons, which we shall also talk about at a later date. However, today is about stents. So the problem with balloon angioplasty, which was of course very useful and did pretty well as compared to the alternatives, but there was a problem because almost 1% of patients would have abrupt closure after angioplasty. Early recoil was seen in 5 to 10%, and a large number of patients, almost half the patients, would see restenosis. So it was obvious that a certain amount of research and some device was required to keep these vessels open. And this was achieved by Julio Palmas, amongst others. Of course, the early steps towards stent design were taken by the redoubtable daughter himself, who also pioneered the use of nitinol for the construction of stents. But of course, his stent designs, though the ideas were sound, the designs never saw commercial application, and they had some problems. So Julio Palmas was the first person to achieve success in stent design. And then onwards, stents have become ubiquitous. To get to the meat of the issue, now there are two kinds of stents that we use: balloon expandable stents and self-expanding stents. And I shall be talking about these in a very detailed manner. Of course, I don't think it's possible to cover everything that is there to know about stents, but I shall try to do justice to a basic principle that we should all be aware of when we use stents. Okay. Now, stents are bioimplants. They are permanent implants, most of them. There are retrievable stents, but I shall talk mainly about the permanent implants. So the materials that we use have to meet the standards for biocompatible materials, which means they should not cause problems in contact with biological tissues. They should have appropriate mechanical properties for the purpose. For example, a bioimplant like a hip joint implant has a different need of mechanical properties as compared to, say, a vascular stent or a heart valve. So each area needs its own specific properties, and those properties are met by a wide variety of materials being used. Then anything implanted in the body which is going to be there for throughout the patient's life has to withstand corrosion, because biological environments are electrolytically active. So any material in there can undergo chemical, electrolytic, and various kinds of corrosion. So the materials used have to be corrosion resistant. And last but not the least, it should be possible to use it at a reasonable cost. There are many materials which are wonderful, but which are so expensive that any device using these materials would be prohibitively expensive. Now, when we talk about these mechanical properties, what are the principles of materials that we use in making stents or engineering in general? So when we talk about any material that undergoes stress, that means when it faces a force in certain directions, you can plot stress, which is the amount of force it experiences versus the deformation that it undergoes, which gives us something called the Young's modulus. Now, up till the point at which the material starts giving way and therefore changes shape, we get a straight line, right, of deformation. But at certain point, that deformation becomes persistent. That's called the yield stress, or the yield point of the material. Okay, and this is a static property of the material. Beyond that point, the material will resist stretching or changing, and that is called tensile strength. And at a certain point, the material will break, and that's called the fracture point. The so-called famous Young's modulus is the curve that is attained by plotting increasing force against the degree of deformation that occurs. Now, it's important to understand this clearly, because in stents, this is very important. And as we go along, I will try to explain why this is so. Basically, stents have to be in an environment which is inherently dynamic, sees movement, pulsatile movements, all kinds of movements, and it has to prevent the vessel from recoiling. That is its primary purpose. Therefore, the strength of the material and its response to repeated and oscillatory forces, etc., is very important in choosing which materials to use for constructing our device. Okay. If you look at a stent, it's a three-dimensional device. So other than the fact that there is the stress and strain and Young's modulus, there is also the appreciation that these properties have to be considered in a 3D manner. So when we talk about self-expanding stents and balloon expandable stents, they are a little bit different. Self-expanding stents has two properties which are not so in balloon expandable stents. Now, the self-expanding stent has a resistance to a compressive force. To a certain extent, it can resist compressive force and re-expand once the force goes away, even if it contracts a little. That's a property that self-expanding stents have, and balloon expandable stents don't have. And this leads to why the differences and the reasons for choosing one kind of stent over the other for a given application. Secondly, a self-expanding stent will try to attain its nominal diameter throughout time. A balloon expandable stent depends upon the expansion of a balloon to achieve its diameter and keep the vessel open, prevent recoil. Whereas the self-expanding stent has its inherent capability of expanding and keep expanding. Therefore, the chronic outward force, or the COF, is dependent on the oversizing. So the degree of oversizing that you give to the self-expanding stent as relative to the expected diameter of the vessel is very important. That's why sizing is critical in the use of stents for a variety of reasons. Secondly, certain areas, the stents are exposed to outside compression. For example, the femoropopliteal region, or say in the carotid. And if you put a balloon expandable stent there, once the hoop strength or the ability to withstand compression is crossed, the stent will collapse. Whereas an elastic self-expanding stent will not collapse, but will re-expand after getting compressed. Okay. So if this is clear, I'll go on. Now, when we talk about the mechanical properties of stent, it's important to understand that the mechanical properties are not uniform throughout the stent, and the mechanical properties are very dependent on the interaction between the stent's expansile force and the lesion's resistance to that force. So if you look at the stent as opposed to a lesion, as you can see in the diagram here, the force of expansion is more in the center where the diameter is narrower, and towards the lesion's edge, it becomes less. Now, if you use a stent which has a narrow diameter range, that means the stent is very close to the diameter of the vessel that you want to achieve. The outward force is going to be less. But if it's got a bigger diameter, then the outward force is going to be more, right? Now we talk about how stents are made a little bit. I know this is not what we do, but we should know about this because stent manufacture is something we should understand. So one way is to take a wire and braid it. This is how a lot of stents are made in the self-expanding variety, even some balloon expandable stents. They can be braided like making cloth, or they can be knitted like making a sweater. The latest technology, of course, is something called additive manufacturing, out of which one is powder bed fusion, in which you heat the substance and deposit it in layers to construct the stent. And this is the most modern manufacturing technology. This can be done using electron beams, using lasers, using other kinds of radiation to heat successive, very, very thin layers of material laid down. It can be done with both metallic materials and non-metallic materials. It is something like 3D printing. It's a variety of 3D printing, I would say. Then, of course, there is the laser cutting, which is perhaps the commonest thing in use, the simplest thing in use for making stents right now, in which a tube is taken and is cut using a very sharp laser, a laser to heat and remove parts of the tube to create a shape that we need, right? So now these are two terms in common use, and the upper row is of balloon expandable stents and the lower row is of self-expanding stents. So closed cell versus open cell refers to a unit of the stent. If you look at any stent, it has recurring units which are used to make the entire stent. The same structure is repeated. That structure is the cell. Now, if the cell has a complete enclosure, like you see in the top, on the left side in both the designs, the upper one is basically a Palmer stent, a Palmer short stent to be precise, and the lower one is an exact stent from Abbott, which is used for the carotid. Both of these, the exact stent is a little bit of a hybrid, but you can see the cells are closed, completely enclosed by metal. Even in the lower one, it's completely enclosed by metal in this case. Of course, the material may not be metal as we should talk. The other kind is the open cell, where you can see each unit has open parts which are not completely enclosed by the material. So open cell versus closed cell. Closed cell and open cell are the two big types of stent design, whether we're talking about self-expanding or balloon expandable stents. That's an example of an open cell stent, something like a smart stent, which is Cordis, right? So the implications of this are a legion. The closed cell structure tends to be stronger as far as longitudinal stress is concerned, but it also is a little less flexible, it tends to be more rigid. Okay, so there are advantages, disadvantages to both of them, depending on the application you have for them, and that has to be considered. Now, when we talk about stent geometry, that's very critical, and there are many different kinds of stent geometry which are used, maybe not necessarily in the vascular world, but almost all of them are in use somewhere or the other. For example, the coil stent is something that's not used. Incidentally, this was the first design which daughter made for a stent, which was a simple coil of nitinol metal. But the coil stents are in use in some urological applications where you have these memotherm stent, which is used for urethral strictures, which can be removed by simply being pulled at a low temperature. It can just be pulled out as a single strip of nitinol. And you have the helical spiral geometry. You can see this is a continuous spiral down below a balloon expandable stent, which is there. But these are not in common use for vascular stents anymore. These are common woven stents, of which there are two types. The more common braided variety, and braided stents have made a big comeback after the wall stent because they have certain properties which are very useful in given conditions. For example, the supera stent, which you see in the middle, is specifically meant for use in the SFA and across joints. And that has got a lot of kink resistance, deformability, etc., because of its braided structure. It's able to accommodate varying diameters, accommodate pulling as well as compression in longitudinal axis, that means along the length of the stent, as well as in the radial axis. Knitted stent, this is a ZA stent by Cook, not in common use. This is made of tantalum. So as you can see, it's a wire which has been knitted to make a stent. These designs are not in common use anymore. Then there are, of course, individual rings, basically these stents, like these are mainly used for stent grafts and not for stents, basically for aortic stent grafts mainly. As you can see, each stent structure is independent from the next. There's no connection between the multiple stents that are within the fabric. These are basically used in stent grafts as support stents, and don't see much use anywhere else. The other kind of stent geometry, which is probably the most common one, is in terms of sequential rings, which are connected with struts or bridges. Now, these rings can have closed cell geometry or open cell geometry. So this, if you look at it, is one ring, and this is another ring, and these two are connected by connectors. Now, the complexity of design can undergo, this particular design can undergo is a lot. You can have connectors of different shapes, V's, N's, Z's, asymmetric connectors. You can have these connections from peak to peak, like in this tent, or from peak to valley, from here to here. This is a valley, this is a peak, or you can have mid-body connections. And all of these have the advantages, disadvantages, right? I shall not get into total detail of each. Theoretically, there are differences between each, but basically what this design does and what it's meant to provide is, unlike the Palma short stent, which is a complete closed cell design, this gives you more flexibility while retaining the desired longitudinal and radial strength to oppose the forces that it's going to face through its existence. Okay, so this is probably the commonest stent design geometry that is in use. Now, this is the slotted tube geometry, which is the Palma's stent again, a simple tube which is cut into this shape, and when expanded achieves this shape, a series of closed cells which are linked to each other. It is very strong and really good. For example, we can use an open Palma stent to extend the landing zone of an aortic stent graft in cases where you feel that it's too small. We use a balloon expandable Palma stent in the aorta to hold that aortic stent graft in place. So that tells you this is a really strong stent, but it is relatively rigid, which is why the Palma short stent came as two short Palma stents with connectors, okay, to give some degree of flexibility. Okay. The radial geometry is basically the Jantarko-Rubin stent, which was actually the first stent which was given commercial approval for coronary use by Cook, and it basically had a radial geometry. Now, to talk about balloon expandable stents first. The design principles and how it matters to us. So basically, each component of the stent that we can talk about has a clinical correlation, has results in some clinical properties. So what metal you choose matters to the radio opacity, how thin you can make the strut, because the thinner the strut, the better, because the less the inflammatory or injury response of the vessel. But the thinner the strut, the less the radio opacity also, and the less the strength. So the crush resistance becomes less as you reduce the strut thickness. So maybe by changing the material from steel to say cobalt chromium or platinum iridium, which we should talk about, you can reduce the strut thickness while maintaining the properties that you need. Of course, all this correlates with the restenosis rates, the inflammatory response of the vessel. And of course, the metal also impacts the allergic and immunological response of the body. For example, nickel allergy occurs with nickel containing materials, not with other materials. The cell size and design will determine how much metal is in contact with, say, the plaque and the wall of the vessel, and that will decide whether the plaque can project through. For example, they say that in the carotid stenting, it's better to use the closed cell rather than open cell design in symptomatic patients, because the plaque stabilization is better with the closed cell design, because more metal is keeping the plaque in place and supporting the plaque. If you have wider open cell design, then the side branch access is easier through the open cells than through the closed cell design. So, and if there's a drug delivery design stent, which we shall again discuss, then the cell design impacts that. The connectors and the design of the connectors impacts the longitudinal strength. That means if the vessel tends to stretch, get pulled in different directions, what happens to the stent? Does it deform too? Does it resist deformation? And if it's deformed, does it go back to the previous dimensions when the force goes away? All that is decided by how the connectors are designed. The flexibility and trackability of the stent also decides that. Okay. So this is a rather busy slide, and there's a lot of information. I try to, keep it to the main points that are important. So basic, two kinds of materials are available for balloon expandable stents, bare metal stents, which are stainless steel 316L, which is a nickel containing steel, which has a lot of desirable properties. Then there is cobalt chromium stents. So these are both very commonly used for balloon expanding systems. Cobalt chromium is a little more expensive, has become more popular because of corrosion resistance, more stiffness, so you can make thinner struts. And but some people claim it gives rise to higher in-stent restenosis. Data is not completely clear on this, but very popular coronary stent Zions is the cobalt chromium stent. A lot of renal stents are cobalt chromium, and a lot more balloon expandable stents are becoming cobalt chromium as compared to 316L steel. Platinum chromium is even more radio opaque, higher strength, but of course it is more expensive, platinum being a more expensive metal, and so that is in use in some stents, mainly in the coronary world. Tantalum has been used for stents earlier, but right now it's of historical interest only. There's hardly any tantalum stents available in the market today. So the other part is that all these materials undergo surface modification, because the surface, if you keep a pure metal surface, that tends to get oxidized and corroded faster. So actually all these stents have a layer of metal oxide on them. For example, like aluminum vessels have, which protect the aluminum from reacting with the environment. Similarly, all these stents have a metal oxide layer on top by surface treatment that prevents corrosion and also supposedly prevents platelet aggregation because it's not a charged surface. This also undergoes more treatment to keep it smooth, to polish it to a high smoothness to reduce platelet aggregation and thereby thrombus formation. That is about the materials used for making stents and their treatment. Now, with self-expecting stents, there are two kinds of materials that are used mainly. One is LG alloy, which was designed for use in the aviation industry, and so it was a very expensive, it's super alloy, very strong. You can see the composition there, but hardly matters beyond pointing out they all contain cobalt, chromium, and nickel. And this was used to design the wall stent, and that is still in use today. It was the first self-expanding stent really came on the market, and it's still in use today, and we are all familiar with it. And it gives it a lot of crush resistance, good radial strength, but it is used to make only braided stents, so it suffers from the advantages and disadvantages of braided stents as compared to laser cut stents. Nitinol is probably the most popular material now for self-expanding stents. Almost all the other stents are made of nickel titanium. It's a shape memory metal, which means it has got two forms, and the transformation occurs at a certain temperature. It's called a critical temperature. The austenite form and the martensite form. And nickel titanium, the transition point is near the body temperature. So it's a super elastic metal, has shape memory, so it expands to attain its size. So you can create it at a particular size, then restrain it into a smaller profile for inserting into the body for deployment. It's usually deployed by pulling back the covering sheath. It has a lot of fatigue resistance as compared to stainless steel. So you'll notice nitinol wires are far more resistant to changing the curve and shape as compared to stainless steel wires. But of course, they contain nickels. So nickel cytotoxicity and allergy are both things that can happen with the material. Woven braided nitinol has now become very popular for making stents like, say, the Supera, or a wide variety of stents meant for use in the neurovascular circulation, which will not be the primary focus of this talk because the talk would stretch forever and more if we got to every kind of stent that exists. So basically, we have discussed the materials for bare metal balloon expanding spill stents and self-expanding stents. Now, these are the examples of woven braided self-expanding stents. The wall stent is the premier example, and what you learn from using, anybody who uses the wall stent will tell you, the problem with braided stents is the final length of the stent depends on the diameter you allow it to expand. Supposing you put a 10 millimeter stent into an 8 millimeter vessel, it's not a problem, but the stent will become longer. So if you have a vessel with varying dimensions, then the stent accommodates it very well, but the final dimension of the stent is hard to tell until you are actually deployed it. So the wall stent has one big advantage. It is partially reconstrainable. So you can deploy a bit of it, then reconstrain it. And that is required because deploying a wall stent perfectly, as anybody who's done a tips with wall stent will tell you, is a very difficult job and needs some experience. The Supera stent, of course, is a braided stent with nitinol, made of nitinol braiding, and displays all the advantages of braided stent. And similarly, like the wall stent, I'm sure if you come to a complication meet, you'll learn about the fact that the Supera stent length is again very difficult to predict when you're deploying it. What the final length will be depends a lot on how you deploy it. Flow diverters, common use in neuro, also mostly braided, and a lot of intracranial stents which are meant for supported coiling, also braided in design. To compare balloon expandable stents with self-expanding stents, the properties that I've spoke about actually tell you what advantages and disadvantages they have. So the production system is completely different. The balloon stent, expandable stent, is manufactured in its narrow state and expanded. The self-expanding stent is manufactured in its expanded state and then crimped. So it's sort of reversed. With the balloon expandable stent, even if you have a narrow vessel, you can dilate it by the force of the balloon, which is expanding it. So a lot of times we do direct stenting with the balloon expandable stent. Even with the self-expanding stent, if the lesion is not too narrow, though this says that predilation is mandatory, it is not really mandatory. It depends upon what kind of lesion you're talking about. You can always post-dilate also, as long as the lesion is wide enough that the deployment system can be removed after the stent is deployed. Okay. So self-expanding stent, but quite often self-expanding stents are used in areas where predilatation is done before the self-expanding stent is deployed. The third thing is that the balloon expandable stent, after you expand it with the balloon to the full diameter, it narrows down a little bit after that. So that is something which is the opposite of self-expanding stent, which will keep expanding to try to achieve its actual diameter even after the balloon inflation is over. So the same property is in the next line, that the proper oversizing will lead to chronic outward force in self-expanding stents, especially more with nitinol stents. The big difference between the two is that a balloon expandable stent has a hoop strength. That means it will resist pressure applied in the radial direction, which is compressing it. But if the hoop strength is exceeded, it will buckle, and that buckling is irreversible. So we never use a balloon stent in areas where there can be a compressive force applied to the stent. For example, in anywhere below the groin, you never use a balloon expandable stent. You always use, if you have to use, you use a self-expanding stent. Similarly, in the carotid, we use a self-expanding stent, never a balloon expandable stent. But inside the body cavity, where there is a skeletal system or something protecting the stent, a balloon expandable stent makes sense. The other parts which are important is, it is very possible to very precisely place a balloon expandable stent. However, a self-expanding stent, the millimetric precision in placement is very difficult, because the force of its expansion tends to move the stent in the axial nature. So most of us will deploy it partially, then adjust the position, then release it fully. So these are the important differences. So in an ostial location, most of the time, a balloon expandable stent will be used. When you are stenting a branch which is at its origin, like say the renal artery or subclavian artery or say celiac or SMA, you will use a balloon expandable stent preferentially. The other thing with the balloon expandable stent is, because of its design and its lack of flexibility, there's an inherent maximal length to which a balloon expanding stent can practically be made. And that is usually, I mean, there's almost nothing which is more than, say, roughly 57 or 59 millimeters. Longer than that, balloon expandable stents in common use are not available. Whereas self-expanding stents can be made much longer. There are 200 millimeter long self-expanding stents meant for the SFA, for example. So this is another difference between the self-expanding stent and the balloon expanding stent. To point out, each has its advantages and disadvantages. And when you are choosing to use one particular variety of stent for a given situation, you should be aware what the potential advantages and disadvantages of using that particular stent can be in that location. Okay. So to summarize, balloon expandable stent gives you good hoop strength, easy radial expansion, precise deployment, but it will not be of very long lengths, not more than 5-6 centimeters, and it will not resist a compressive force beyond a certain point. And if it buckles, it completely loses function. It's not going to recoil after that. Self-expanding stents, more difficult to deploy precisely, and they will always have a chronic outwards force. So which also means if you oversize it, it will continue to try to expand the artery beyond the diameter that you'd like to have. Okay. So as they say, nitinol stents will achieve their nominal diameter, whatever time it takes, even if it is much bigger than the vessel you put inside. Okay. Third thing, if you have a very long stent requirement, perhaps self-expanding stent is what you need. This was as far as the mechanical aspects of stent design are concerned. Okay. But we know that the human being is biological, and though we look at everything very mechanically, talking about forces and engineering-like solution, but actually, whenever you put the stent into the body, there's a lot of response the body has to the stent. For example, the coagulation cascade can get activated because the stent surface gives rise to platelet aggregation and thrombus forms. Certain materials are more prone to thrombus formation than others. Endothelial injury, of course, happens when you place a stent because the stent is pressing and resting on the endothelium. When you forcefully dilate a balloon expandable stent, perhaps the endothelial injury is a little more than when you gently release a self-expanding stent and that slowly expands over time. Then there can be immunological phenomena because the stent is, after all, a foreign body. And immunological response to any foreign body over time is somewhat inevitable. Then, of course, the hemodynamic forces and endothelial responses to the stent and its deployment are very important to understand. So there are early responses, midterm responses, and late responses. I mean, you can have, and these can happen throughout the wall of the vessel, as shown here. And I'm mainly talking about arteries, but some of what I say applies to veins as well, only in a different manner because veins tend to be much larger when you're using stents. So the results can be different. Now, vascular injury, including dissection at the edges of the stent, can happen. There can be thrombosis in the early stage. In the middle stage, the main thing we are concerned about is the response of the endothelial cells conversion to smooth muscle cells, thereby neointimal hyperplasia. Within 3 to 6 months, it will start off and peak. Then over a longer time, there can be inflammation and delayed reindustrialization. And especially in stents which are chemically active, that can be something that is hard to predict. And the response of the endothelium to that may not be known for some time. Why this is important to understand is because when you put in the stent, it's a foreign surface. Over time, it gets endothelialized. And this endothelialization leads to the struts getting buried under endothelium, which is now not reactive, which will not cause platelet activation, which is the normal surface that the blood is in contact with. Okay, and that's a desirable state. But if you have inflammation and thereby delayed endothelialization, then that surface remains a foreign surface and not friendly to platelets and can be thrombogenic, even in delayed. So you can have late thrombogenicity as well, depending on the material that stents are made of. Okay. These are some images to show how it's important, how the surface is prepared. On the A side is an electropolished surface, which is routinely done for vascular stents, and the other side is non-electropolished. You can see how rapidly, over a difference of like a few minutes, the thrombus has formed far more on the non-electropolished surface as compared to electropolished surface. So other than that, if the stent is not properly deployed, there can be hemodynamic alterations producing other problems and increasing homogeneity as well. Okay. So surface coating is also done in non-vascular stents in many cases. For example, in GI stents, etc., silicone coatings have been used, biliary stents, to change the surface response. So we will hear a lot of talk about hemodynamics, and I thought I would just talk a little bit about hemodynamics, the basic principle and the strength, because the endothelial cell responds to something called the wall shear stress. So what is this wall shear stress? We know that the blood vessel, the blood in the blood vessel, though we treat it as an ideal fluid, even if we do, does not move at the same velocity in all parts of the vessel. This diagram is trying to show that if you take RBCs, for example, which were here to begin with, after time t, if you measure the same RBCs, the central ones would have moved farther, they're traveling faster than the ones near the wall of the vessel. Of course, there's a gradient of velocity from the wall to the center of the vessel. Okay. And the rate of change of velocity with distance from the center or from the wall is the shear rate. So This is nothing but telling you what is the difference in velocity between the middle of the as you approach close to the wall, how much slowing of blood flow is happening. That is the shear rate. Now, the viscosity of the blood multiplied by the shear rate is the wall shear stress, because that tells you how much of force along the direction of blood flow the endothelial surface is experiencing. It's all very, theoretical sounding, but it matters. And research has shown that it's really important to take wall shear stress into account. And animal research as well as in vitro research has shown that the endothelial layer is highly biologically active. It is not something inert like a coating. It's all cells. And the cells have signals which they receive and actions which they carry out, proteins which they release, and enzymes that get activated. All this complexity, and not going into details, the simple fact is that there are three possible states of wall shear stress, and all of them have different effects on the endothelium. And when you put a stent into a vessel, you will alter the wall shear stress, and differently in different areas. So if you deploy the stent correctly, choose the right stent the right area, you can mechanically minimize the alterations in wall shear stress as compared to a badly deployed, incompletely expanded stent. So to make it clear, now the chart on the right is of course very busy and very complicated, but to put it simply, there are low wall shear stress areas, there are high wall shear stress areas, and there are oscillatory wall shear stress areas. So when each of these has different responses achieved from the endothelium, and the plaque formation, you realize, occurs on the carotid bifurcation. We all know that. And we have said, it is because there's flow separation, there's whatever. Ultimately, it's the fact that the endothelial response to the change, the flow separation into the ECA and the ICA, the high flow of the ICA and the little bit of turbulence which occurs at that bifurcation is what gives rise to more plaque formation there, because the endothelial response is changed in bifurcations, right? And when you have oscillatory flow or turbulent flow and bidirectional flow, that is even worse. It can cause a lot of problems in the endothelial response. Okay. So this is why we care about this, because then we know that if you don't match the diameter properly, okay, if there are spaces where the wall is not properly opposed to the wall, if there are parts where the diameter changes abruptly in the stent, then there will be a hemodynamic response in the wall shear stress, which will give rise to problems like thrombogenicity, endothelial hyperplasia more, or plaque formation even. Across curves, when we take stents, the stent should try not to alter the curve as much as possible. Of course, sometimes it's impossible not to alter the curve. But all these changes that we make to the normal anatomy can give rise to problems and alterations in wall shear stress patterns. And that can lead to thrombosis, plaque formation, intimal hyperplasia, and all these different endothelial biological responses. The most obvious part of this is the injury response. Basically, whenever we do an angioplasty, we injure the intima, we tear through the intima, we rupture it, sort of. And there's an inflammatory response, the neutrophilic infiltrate, leukocytes come in. And what it leads to is something that we call smooth muscle cell proliferation. And if there's sufficient, then it gives rise to what we call instant restenosis, lumen loss, intimal hyperplasia, neo-intimal hyperplasia, which is something which is the bane of stent design and which we are still fighting with after all these years. The diagram shows what happens in this. Smooth muscle cells form multiple layers, migrate across the media and get under the intima and cause neo-intimal hyperplasia. Lots of smooth muscle cells. This is the rubbery thickening of the wall, which narrows the vessel. And that lumen loss, which usually occurs between 3 to 6 months after the placement of the stent, it was the bane of stents, particularly in coronary arteries. And that's why a response to that was really necessary. So if you look at the time and the response, you can get 1 month thrombus formation. It's early thrombus, immediate thrombosis, late thrombosis up to 1 month. At 6 months, you can get instant renosis as well as thrombus formation, and neo-intimal hyperplasia, which progresses from 6 to 12 months. Okay, and that you can lead to stent failure. Of course, instant restenosis can be edge restenosis, complete restenosis, partial. There's a lot of gradings, fancy terms, not part of this talk. to talk just about what we have spoken about so far, the geometry, the stent materials, etc., how this affects everything is something this diagram is trying to put across, which is to say that the stent alloy that you use and the strut thickness, which affects all these factors, the radial opacity, the strut thickness, radial strength, and the recoil. And that gives us all these things that we have to figure out. So it's very important to understand how the particular stent design that you're using in a given environment is going to affect just the sheer mechanical stability of what you're trying to achieve. Okay. So whether you can get to the area you want to get to, if you take a balloon expandable stent and try to enter the cerebral circulation beyond the, say, the carotid siphon, it's going to be extremely challenging because they are too stiff. Even coronary stents can become very challenging to put there. You need a lot of support to do that. Whereas a self-expanding stent, it is much simpler and easier. So on and so forth. Visibility of the stent, as you use stent alloys which are not so visible, you have to put markers. Those markers are attached to the stent, which increases the cost of manufacture of the stent, etc., etc. So all these factors are very important in how a stent is used, how you select the right stent for the task that you have at hand, and what the long-term impact of that stent is going to be. So the problem of in-stent restenosis that we spoke about, intimal hyperplasia in other words, was basically that of cells dividing to narrow down, thicken the wall of the artery, narrow down the lumen, and lose the benefit that we gained by deploying a stent. So the solution was to use drugs that stop the inflammation and cell division. Now the first one to be used, a lot of drugs, but the first one to be used was rapamycin or sirolimus, which came from a bacterium of the Streptomyces genus. And basically that drug acts on something called mammalian target of rapamycin, which stops cell division, right? In the G1 and the S phase. And there are a lot of variants now of the similar drugs. Then the other drug which came in almost simultaneously was paclitaxel, which stops microtubule growth, which are very important, as we know, for cell division. So both these are immunosuppressants. They are used for treating cancer and they are used for treating intimal hyperplasia. So obviously these drugs can have serious side effects in high doses, right? So how to use them for intimal hyperplasia was basically that you put the drug on the stent. So now when you put the drug on the stent, you understand that the process of intimal hyperplasia, the injury and the injury response is not happening soon. It's happening over a long time. So obviously the drug has to be deployed over time. At the same time, the drug should not extend too much in the systemic circulation. So it should have a short half-life. So what do? You attach it to the stent either by putting it into a polymer, which slowly releases the drug. That polymer can be something like, say, cyanoacrylate based, which is a permanent polymer coating the stent into which the drug is bound and then gets released. But the coating, the permanent coating, remains on the stent. Or then this coating was implicated over time in causing problems with the stent again. So they came up with biodegradable polymers, which are basically PLLA, lactic acid based, or other compound based, which are biodegradable, which would release the drug over, say, 3 to 6 months and then disappear. Now, the newest technology is to have no coating, but to put the rapamycin, the sirolimus, or the other paclitaxel or the other drugs on the surface of the metal itself by using nanotechnology to create some microporous surfaces on which the drug is kept and slowly gets released over time. Okay. So it is very important to understand that an immediate injection of a drug is not going to do much. You need a slow, prolonged release over a time, inhibiting the intimal hyperplasia over a long time. So does this work? Yes, it works. At least in the coronary circulation, it works very well. It brought down the incidence of restenosis from 20% to below 5%. In the peripheral circulation also, we know it works. It is not perfect, not saying it has solved all problems, but it works better than bare metal stent. It's a little more primary patency than a bare metal stent. So perhaps this is the way to go. Okay, so to summarize the drug elution idea, the basic thing is a stent, a scaffold, which can be metallic or biodegradable. The anti-proliferative drug, various kinds, paclitaxel, rapamycin, Zotrolimus, etc., 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 and you attach that to the stent with the delivery vehicle either directly on the metallic stent or the scaffold or with a polymer. Usually now they prefer biodegradable polymers in the newer devices. But all this is fine. But the metal stent stays in the body as a permanent implant, even though its usefulness is over a period of say 3 to 6 months. After that, you don't really need it. The vessel is okay, it's open, and the presence of that foreign body will continue to elicit an immunological response and perhaps create problems in other ways. Because after all, it contains a lot of metal inside the body. So ideal thing would be to create something which is resorbable. And yes, it has been done. We know that bioresorbable stents have been created. And these should disappear when the job is done, matching the duration of the biological response. Please note this line, very important. It should not disappear too early. It should not disappear too late. The ideal time depends on, will have to be said with research, but between 12 to 24 months is what is considered the ideal time of resorption. The other parts, the resorption should not happen in a patchy manner. It should happen globally. You can't have one strut of the scaffold suddenly being reabsorbed and other part of the thing still remains. That will degrade its mechanical properties and might lose function early. And this is a problem which did happen with some materials which were tried. Okay? So slow surface resorption better than bulk degradation of the material that the scaffold which is made of. And very importantly and more difficulty, material properties should be compatible with stent function. That means it should match at least the currently existing metallic stents in terms of trackability, crossing profile, radio opacity, radial force, hoop strength, and all the things we spoke about. Okay. So there are basically two kinds of materials which are in use. There's the polymers and then the metallic ones. The metallic one is basically the magnesium alloy. The problem with magnesium has been that it probably gets resolved too fast. Biotronic has a device. It has got good visibility. It's got thin struts. It's very good in other ways, but it seems to get resolved a little too fast. So maybe it's not the ideal material yet. So they came up the other material, which was basically polylactide, PLLA, which was used to make resorbable sutures earlier also, which gets absorbed over 12 to 36 months. There are lots of variants of this polymer basic one. The problem with this has been to get the same radial strength, hoop strength, etc., and radio opacity, you need to have thicker struts. So it tended to be rigid. Everybody who used the coronary stent for absorbable the scaffold stent complained about the rigidity of the stent and difficulty of taking it to the right place for the higher crossing profile. They also have a magnesium PLGA hybrid, which is a mixture of the polymer plus magnesium. And there's a tyrosine analog polymer, which contains iodine. So it is inherently radiopaque, but that's still in development. So I don't think it's commercially available yet. So these are the materials now which are probably pointing the way to a bioresorbable scaffold future for stents. Various things which are in development or commercially available. This does not really mention the big Indian achievement of the MRES 100, which is a bioresorbable drug-eluting scaffold from Merrill, which is an Indian company available for the coronary. I believe trial was done for the peripheral device, but I don't know what the future of that is in the commercial world, whether we're going to really see it being made available commercially or not. So what are the problems with these resolvable scaffolds? They're not without problems. So late thrombosis has been a problem. So most of the time with most of these scaffolds, the instructions for use ask us to continue dual antiplatelets for longer than with usual stents. Mechanical properties have been questionable as compared to cobalt, chromium, and platinum cobalt stents. Again, the resorption has not been completely predictable, perhaps because of individual differences or manufacturing practices. Radio opacity has consistently been a problem for these stents. So to summarize just this, over time, how stents have grown and changed, and I'm talking basically about vascular stents, from the BMS bare metallic stent of basically the Parma stent and the wall stent and nitinol stents to the drug-eluting metallic stents, to the polymer which was permanent, the polymer which became biodegradable, and now drug-eluting fully resorbable stents are possibly the future of stents. And as you can see, the usage of drug-eluting stents has been consistently increasing in the coronary world. Of course, it's the preferred stent, But even in the peripheral world, slowly drug-eluting stents are making space for themselves. But we are hoping that we'll get something which will be completely resolvable. So we'll be much more free with our use of stents. Thank you. Whatever questions are there, I'll be happy to answer.
Thank you, sir, for such a wonderful and inspiring lecture. Most of the points have been well covered and well received by our audience. And now forum is open for any discussions. Sir, if none, I will ask few questions to you. And can you please elaborate about vasculomimetic stents?
The vasculomimetic stent is basically a specific design of a self-expanding stent. It's braided. And basically the problem has been in particularly the femoropopliteal segment below the groin, that those arteries are extremely mobile. They undergo multiple forces and deformation. So the usual laser cut stents have not done so well there. There's a high incidence of strut fractures. The intimal hyperplasia has been marked in some of these. In fact, personally, I try to avoid stents in this region wherever I can, but sometimes you don't have an option. Now, the vascular mimetic stent is designed in a way with multiple wires which are woven in a pattern that allows the stent to withstand compression, which all self-expanding stents do, longitudinal change in length very well as torsional forces, twisting forces, which are peculiar to the SFA and arteries below. So for the reason this vasculomimetic stent is called that because it mimics the movements of the artery. So the usual stent will change the artery to fit itself. This stent is meant to fit the artery in which it's placed. So as the artery moves, the stent moves, deforms, and comes back to shape without losing its opening. So it is, you can say, a design which is very, very elastic. Okay. So, and deformable. So that's been the basically the Supera is one. There's also another vasculomimetic stent which is not available in our country, so can't talk about that. But the Supera has definitely shown better results in the SFA than the other stents, particularly if you're going to the adductor canal region and below that. But yeah, still has some problems.
Okay. In case of total occlusion, how do you choose the stent size? And number two, if you want to pre-dilate, what balloon and what size you would prefer?
So this is a very big question, actually beyond the scope of this lecture. But
yes,
I would say when you are looking at a CTO, so let's take an example. Okay, let's take two different examples. One is say an SFA CTO. One is say an iliac CTO. They're very different because one, the iliac is a bigger artery. Two, the iliac is a well-protected artery, doesn't get exposed to so many forces, got nice, protection all around it. So with an iliac CTO, I could use a balloon expandable, or I could use a self-expanding stent. Now, which one I will use will depend upon where the CTO is ending. Supposing I have got to go to the aortic bifurcation, okay, and it's a bilateral stenting, then the ideal thing is to actually use a stent graft on both sides and do what's called a CRAP, where you recreate the aortic bifurcation using stent graft, because definitely the restenosis and the occlusion rates of that approach is lesser than using two bare stents. My next choice would depend upon what kind of diameter I'm talking about and what kind of position I have achieved. So I will use balloon expandable stents wherever I need to place it very precisely. You are almost at the ostium and you don't want to cross over where you project over the opposite artery. I will use a balloon expandable stent. But supposing I'm stenting both and I'm going up into the aorta in parallel fashion from both sides, I could use a self-expanding stent as well then, because then it's not such a precise, finicky positioning, right? So both options are there. But if you look at the SFA, there's no question of using a balloon expandable stent. It's an exposed area. You happen to, something falls in your thigh, the stent gets crushed, you finished. So that will be self-expanding. Even there, I would say, if you have to stent the SFA, my first choice would be a Supera. Next choice would be one of the other, stents of this thing. And your approach of dilatation, what he spoke about. Now, as I said earlier, balloon dilated stents, you have an advantage. You can pick your size and dilate to that. The problem particularly with the iliac is you don't really know the diameter to which you can safely dilate, because if you over dilate, you get a rupture and that can be catastrophic. So I would say in an iliac, I would tend to undersize a little. Supposing it looks like a 9 or 10, I would just go to 8 or 7 because I don't need a perfect diameter. I just need enough diameter that the hemodynamically is not significant. Whereas getting a rupture would make things much worse, increase the cost a lot. Okay. And maybe there will be an emergency procedure then. So undersize, you can use whatever stent you prefer for the particular location. But in the CTO, I would say it depends upon the area you are in very much. So with a self-expanding, I will dilate to say 5 and then place a 8mm stent. I can oversize a bit, no problem. But a balloon expandable, there's no question of oversizing. You oversize and the vessel ruptures, you are in bad trouble. The patient can crash and die in like minutes.
And regarding the choosing the size of the stent, do you compare with the opposite artery or whatever? I mean, it is
So I would say it would be, I mean, again, it's a territory-wise decision. It's not a one-size-fits-all decision. So if you're talking about iliac, say, if you're approaching the external iliac, it's very different. Now, remember your stent is, if you're using a balloon expandable stent, it's the same size all through. It's never going to be tapered. Whereas if you use a self-expanding stent, you can put an 8mm after a 5mm dilatation. Lower part can expand to a certain size, upper part can expand to a bigger size. If you're coming to the external iliac, then the most vulnerable part of the iliac artery is the bifurcation. That's where most of the ruptures happen. And it happens because at that point, there's a big change of size. Okay. So I would say your selection of size would depend upon your assessment of the arterial anatomy. If you have the other side to assess, look at it, but undersize to it if you're doing a CTO, especially with a balloon expandable. With a self-expanding, you can size the same, but don't dilate to that size. Under dilate, then put the self-expanding stent. You can always go back and post dilate later on if you feel it's undersized.
Dr. Deepak has asked, cobalt stent, is it better, sir?
So cobalt chromium has the advantage of better visibility and thinner struts because it's stronger material. So theoretically, yes, it is better because data has shown that the less the strut size in contact with the intima, the less the intimal response. But practically, does it make a difference? I would say if you're talking about bigger stents, maybe not. If you're talking about 8-10 mm stents. But if you're talking about renal stents, for example, yes, it might be better to use a cobalt chromium stent. But remember, they also cost more. So if you have the option, definitely. But is there a remarkable difference? Probably not. Probably the disease is more important than the stent.
One more thing, sir. Does duration of antiplatelet therapy vary with the different type of stents? And
Well,
what is your experience, sir? It is just for our audience, at least you can give guidelines.
Most of our patient antiplatelet therapy is forever. The only question you can probably ask is, are you going to continue dual antiplatelet?
Yes, sir.
Yes, now there isn't good data on this. It's hard to say something definitely. I'll put it this way: if I've got a stent below 6mm, I'm always far more worried about thrombotic occlusion than 6mm and above. In that case, I'll probably continue dual antiplatelet much longer. Now, that being said, don't generalize because you have to look at your patient's bleeding risk. If your patient has a high Has-Bled score, then continuing dual antiplatelet for longer gives you a higher chance of getting a bleed, which will be clinically significant. So there is no one answer to this question. Okay. With larger stents which have had good results and the artery is not severely diseased, you can probably put on dual antiplatelets, say like the coronary protocol, 6 weeks to 3 months, sometime like that, and then shift toward a single antiplatelet. If you are following the Voyager PAD protocol, then Xarelto is there after that. So actually that dual antiplatelet versus single antiplatelet, there is no good data to support that it's actually better. We do it because of things about resistance. The dual makes sure that there is no resistance, etc., etc. If you're asking scientifically, I don't have a good answer for it.
One more thing, sir. Is there any difference if it is there a arterial stenting versus venous stenting? Do you prefer what about the antiplatelets and anticoagulants?
So with venous stenting, it depends on whether you've done a thrombotic stenting or non-thrombotic stenting.
Yes, sir.
If you've done a thrombotic stenting, of course, the patient is on anticoagulation. If you've done it in non-thrombotic situation, like in some kind of Maytherner where there is no DVT and you put in a stent, I would put them on antiplatelets. If I achieved a good lumen, good position, good size, there is no projection across the opposite iliac vein, I would put them just on antiplatelet, single antiplatelet, and that's it. If
But
the patient has no other indication for anticoagulation.
For venous thrombosis, usually platelet mechanism doesn't work, no, sir.
Doesn't work. But see, this is the minimum. Let me put it this way. There are some trials which have shown that addition of single antiplatelet prolongs patency in various situations. Are they good? Is it good data? No. But a single antiplatelet in most patients is not going to do any harm. So I do put them on that.
Okay, one more question. In case of overlapping stents, what you will put the proximal or distal one first, or what is the overlapping distance you?
The theory is that the distal one should be done first, proximal and next, and the bigger stent always goes inside the smaller stent for obvious reasons. Okay, and the amount of overlaps should be sufficient that even with movement, there is no point where the overlap will dissociate. So if you look at, for example, things which move a lot, say SFA, etc., then you can look at least a 6 millimeter plus overlap, because that will ensure that they don't disconnect because of the longitudinal lengthening. Because disconnection will mean failure, 100%. Ideally, don't overlap stents if you can avoid it. Ideally not, but sometimes we have to. So if you have to, overlap sufficiently. Don't try a very cute overlap. That doesn't work well. Get enough overlap.
Thank you, sir. It was wonderful lecture, and I hope everybody enjoyed this lecture, and it would be very grateful.
Dr. Chandrasekhar, there are few questions. There are few questions in question and answer icon.
Okay, 1 minute. Oh, sorry, sir. Late restenosis rates higher in drug-eluting stents, sir. Answer: is it so?
Okay, late restenosis rates higher in drug-eluting stents as compared to what is the question I would ask. But yes, it particularly in the biosrubal scaffolds, there has been an incidence of late thrombosis. And even in drug-eluting stents of other kind, especially in the peripheral circulation, there is a tendency that you should provide them longer period of anticoagulation before you take them off that. Is there strong data? Probably not. But yes, it is known that the drug itself causes delayed endothelialization. So they tend to be thrombogenic for longer periods of time as compared to standard stents. So if you look at cardiology practice, which probably is by sheer numbers better informed than us, because they do so many of them, they will tend to keep drug-eluting stent people on dual antiplatelets much longer than they would non-drug-eluting stents. So yes, there is some biological reason for it, with the cell division being retarded. The re-endothelialization is also retarded.
What is the difference in radial force between laser cut and braided stents? Dr. Amit have asked.
Okay, so when you talk about chronic outward force and ability to withstand radial force, they are two different things. One is the ability to open up and keep opening up. Okay, now if any one of you has seen a wall stent in use, if you put a 10 millimeters wall stent into an 8 millimeter common carotid, the common carotid will not become 10 millimeter. The wall stent will become longer. That's what happens. Whereas you put a 10 millimeter nitinol stent, that will push to 10 millimeter size eventually. Even if it completely covered and dug into the wall, it will still become 10 millimeters. Right? So in terms of outward force, nitinol is far beyond LG law at least. Now between braided and laser cut tends to have more force because the entire thing is one device. There are no separate wires. It's one piece. Whereas in the braided stent, there are multiple wires, so there is relative movement between the wires. But even there, nitinol braided to that shape will try to achieve that shape with a little less force. So braided stents exert a little less force on the arterial wall. Okay. So if you look at the Supera IFU, before you put it in, you're supposed to dilate to a size about 0.5 larger than the Supera diameter that you're going to place. Okay. That tells you that the Supera stent is not going to exert as much force as the this thing. So if you want to have better lumen after placing the stent, you should dilate it bigger. Okay. I hope that answers it.
Does the buckling after crossing hoop stent lead to stent thrombosis?
Sorry, I'm buckling up. Yeah,
Yes.
if a stent collapses, a balloon expandable stent, that's where the term hoop stent applies. If it collapses, that stent is going to close. It's going to shut down almost 100%. And that's a disaster.
Yes, sir. Sometimes we do subintimal recanalizations in very calcific lumens. In such cases, what do you think the use of these stents in such cases?
Look, ideally, if you're talking about proper subintimal angioplasty, you're not supposed to use stents. And it's a balloon angioplasty procedure meant to treat critical limb ischemia, the target being only wound healing. But sometimes you have to place a stent just to keep it open. If you have to place a stent, you have to place a stent. There's no way around it because it's critical limb ischemia. Presumably, if you're doing this, you're talking about critical limb ischemia. I wouldn't do it for an intermittent claudication. So which stent I would use depends on the area I am in. So, I mean, below the knee, even if you put a stent, it's not going to work too long. You can maybe put in a drug-eluting stent at that point. Maybe a coronary stent is the only thing you will find. If you have to, then you put a point coronary stent in a flow-limiting dissection or something and keep it open. If you're talking about popliteal and SFA, I would use a supera.
Thank you, sir. It was a wonderful lecture, and for my gratitude to whole ISVR team. I am very much thankful to all the participants for attending these master classes, especially during these weekends. Please spread the words about these master classes so that more and more IRs can get benefited. Now, if there is no question, then we can end this session. Thank you very much.
Dr. Rochan, one question from my side. In your chart showing the difference between the balloon expandable and self-expandable, it was written that in balloon expandable, we need not to pre-dilate it. Sometimes it happens that the balloon loses the stent. So
yeah, so these are all what shall I say, relative differences. It's not absolute. There are lesions where you'll have to pre-dilate because it's smaller than the crossing profile of the stent. So that you have to know. But as compared to a self-expanding stent, a balloon mounted stent will achieve its full diameter without the assistance of anything else. That is what it basically is. So most of the time we can do it without pre-dilatation, but sometimes in very tight lesions, particularly in renals, better to pre-dilate. And if you're using a stent graft, please always pre-dilate because the stent graft slides off much more easily than a proper stent. So that a lot of this doesn't apply to stent grafts. They are a different thing. So probably something to talk about separately.
And there are a lot of new developments also, sir, like impregnating stem cells and chemotherapeutic agents in the stents and EGFR, all these things.
In terms of stent coatings, there are lots of research areas, but I don't know how many of them are going to see final practical application apart from the drug-eluting stent, which is a reality, which is going to be there and it's going to go more and more because there are definite advantages to it, especially the bioabsorbable scaffold. I think that will see a lot of action in the future to come. But yes, maybe we can, with the newer nanotechnologies of building reservoirs in the metal itself, you might be able to deliver many things, including, signal transduction chemicals to, block signals for hyperplasia. I don't know. The future is unknown. We don't know what's going to happen. Research is big. Maybe nanomaterials will come into stents and you'll get a stent which is fantastically strong and really, really small. Who knows? And also disappears when you apply electric current. We don't know. So all these are theoretically there, but not practically yet.
Yes, sir. Thank you, sir. Thank you. And
been a privilege.
Yes, sir. Now we will end this session. Thank you all.
Yeah. Bye.
Thank you, sir.